Hello, chemists. This is Ms. Placino, and you're watching lesson 9.2 on calorimetry. In today's lesson, we're going to talk about what calorimetry is and what it's used for. Goals for today's lessons. You should be able to understand and explain how calorimetry works. You should be able to define the system and surroundings. And the big one for today, you should perform calculations using Q equals mc delta T and the first law of thermodynamics. If you are unfamiliar with that formula, go back and watch lesson 9.1 before you dive into lesson 9.2. Again, today's lesson is going to be pretty calculator heavy, so make sure that you have a calculator handy, and your reference table might be helpful as well. All right, let's dive into this. Let's look at some terminology that we'll be using while discussing calorimetry. When we say system, we're talking about the part of the universe being studied. Usually this is like the reaction that you're running or the phase change that you're evaluating. Surroundings is really just everything else in the universe that interacts with the system. More often than not, that's going to be like the reaction vessel and the immediate surrounding areas. So just to try to represent that with a picture, let's say you're running some sort of chemical reaction in an Erlenmeyer flask. The flask isn't actually part of the system. It's just the material where the reaction is taking place. The surroundings that we would study are going to be the Erlenmeyer flask, as well as the immediate area that's kind of in contact with it. So the system plus the surroundings is going to equal the universe. Technically, the surroundings are like literally anything that is not the system. But again, for our purposes, it's going to be most useful to study the immediate surroundings and not, something that's like miles away from the reaction that you're running. The first law of thermodynamics, and you're probably familiar with this law, even though you have not heard it termed this before. The first law of thermodynamics is not that you do not talk about thermodynamics, it's about energy. The first law states that energy cannot be created or destroyed. It can only change forms. You might recognize this as the law of conservation of energy. And they're really, one and the same. You can use the terms interchangeably. So what we're going to see as we study calorimetry is whatever energy the system had before, at the end, whether it's after a physical change or after a chemical change, energy can change and become something different, kinetic to potential, for example, but it has to be the same amount of energy. We cannot create or destroy energy in any sort of chemical or physical change. Yes, you might be thinking about nuclear chemistry. Technically, we do there, but we're going to scale back to just chemical and physical changes at this point in time. So the law of conservation of energy, or the first law of thermodynamics, really gets applied when we're using calorimetry. In calorimetry, we use a calorimeter. Basically, what a calorimeter is a closed, isolated system. You have your reaction vessel, so some place where your reaction can take place. And then you've got it surrounded by water. We've got a thermometer, so we can measure changes in temperatures. If you have a fancy calorimeter, you might have a stirrer that's going to help kind of like just move the water around so that you don't end up with weird hot spots. And a calorimeter is going to just be this device that we use to measure the heat of a chemical reaction or a physical change. We'll actually be doing this in the lab. We're able to use calorimetry, again, because of the first law of thermodynamics. Whenever energy is lost by the system, and our system is going to be kind of whatever reaction or change is taking place in this little sample cup, has to be equal to the energy that is gained by the surroundings. So if we burn something, we're in a combustion reaction, you know from experience that burning something gives off heat. It's going to be difficult to measure kind of like how much energy is getting given off by the flame. Like you can't just stick a thermometer in there, that's going to be tough. But we can measure what happens to the surroundings, in this case, the water. We can kind of work backwards to figure out how much energy was lost by the system, because it has to be equal to the amount of energy gained by the surroundings. Wow, that is some bad handwriting. My apologies, chemists. So that might feel a little abstract at first, but we're going to kind of walk through a calorimetry experiment today, and we're going to apply the Q equals mc delta T formula that we talked about in the previous lesson. Again, really the driving idea here is whatever energy gets lost by the reaction, aka the system, is going to be equal to the energy that has been gained by the water, which is our surroundings. All right, so how can we determine the identity of a metal using calorimetry? What I'd like you to do is pause the video, maybe try to brainstorm on this for 15, 20 seconds. How can we maybe do this? Give it a shot. Think about it. It's okay if you're drawing a blank. You've been studying calorimetry for about 5 minutes, so you're allowed to be confused. Let's see if we can kind of start to break it down stepwise and see if that will kind of help nudge you in the right direction. So we've been talking about this idea that what's lost by the system is going to be equal to the energy that's gained by the surroundings. In this case, our system is the metal, and as always, the water and the calorimeter is going to be the surroundings. So we've got this relationship. Whatever is lost by the metal must be equal to the energy that is gained by the surroundings, more specifically the water. In the previous lesson, we learned what Q is equal to. Q is equal to mc delta T. Okay, so I've got negative mc of the metal delta T is equal to mc of the water delta T. Any idea now how we might be able to identify a metal? You might be thinking, well, can we figure out the specific heat of that metal? And since metals will have different specific heats, can we identify it that way? And if that's your thought process, you got it. We can, through calorimetry, figure out the specific heat of the metal and then compare that to known values and hopefully make an identification of our unknown metal sample. So let's give this a shot. How we're going to collect the data. Let's start with a metal sample. So that's something like this. And we know that we're working with mc delta T. We're, of course, still trying to find C. So I'm just going to put a little question mark over that. That is going to be our unknown. How can I find the mass? Yeah, easy. Put it on a scale. Delta T. Does it make much sense just to put a thermometer like touching the metal? Probably not. Might be stuck here. Here's a hint. We have a beaker of boiling water. Remember, we're talking about delta T. We need a T initial and a T final. Oh, what if you put the metal in the boiling water and you let it hang out there for a while? What's going to happen to the temperature of the metal? Hopefully we're thinking it's going to increase. Increase to what? Well, water boils at 100 degrees Celsius. We know at its boiling point, the temperature is going to remain constant. So if we put that little block of metal in the boiling water, our initial temperature will be equal to 100 degrees C. Final temperature, we can figure out from the calorimeter. Let's go through that same thought process for the water that's present in the calorimeter. So just to kind of remind you, here's what our basic calorimeter is going to look like. We're interested in this water. I guess that's kind of pointing to the thermometer. And I got to deal with Q equals mc delta T. Liquid water, we've got that constant. We know C is going to be 4.18 joules per gram degrees Celsius. I need an initial temperature and a final temperature and a mass. If I measure the volume of the water, I can use the conversion density is equal to 1.00 grams per milliliter. So if I know the volume of the water I've put into the calorimeter, I can very quickly figure out its mass simply by changing units. I can take the initial temperature, just use the thermometer. I can take my metal out of this hot water bath. I can stick it into the calorimeter. And what should be true about the temperature of the metal and the water when, kind of this process is complete? Yeah, ultimately they should end up equaling one another. So I can get my final temperature from the calorimeter. Just use that thermometer. So this might seem a little complicated. You will be kind of walking through this in the lab. I don't really have a video showing you of like boiling water and putting the metal in there. So we're just going to assume we go through this process. Take the mass of the metal, heat it up to 100 degrees Celsius, transfer it to the calorimeter. I know how much water I used, and I know the temperature, the starting temperature of that water. I'm going to put the metal block in there. I should see an increase in temperature of the water. If I just kind of let this thing sit until the changes in temperature stop, I'll measure my final temperature, and ultimately I should be able to work backwards to figure out the specific heat of the metal. I know this sounds like a lot, but we're going to be able to get through it. All right, so let's assume that we went to the lab and we'll start to give you some hypothetical data. I put the metal on the scale. I got a mass of 40.5 grams. I don't know the specific heat. That's what I'm trying to figure out. I'm going to leave that as X. I had taken the metal out of the boiling water bath, so I know that the initial temperature of the metal will be 100 degrees Celsius. We'll deal with final temperature in just a moment. The mass of the water. Well, I'm going to find the volume of the water. I used a graduated cylinder and I measured out 48.0 milliliters. Water has a density of 1 gram per milliliter, so 48 milliliters would have a mass of 48 grams. The specific heat of water is a constant, 4.18 joules per gram degree Celsius. I just looked that up off the table. And I measured the initial temperature of the water in the calorimeter, and it was 21.5 degrees Celsius. Once I take that hot metal and I put it into the relatively cool water in the calorimeter, I'm going to see the metal decrease in temperature and the water in the calorimeter increase in temperature. Ultimately, they'll end up at the same temperature, which was measured to be 27.7 degrees Celsius. Sorry. All right. So we can start to try to kind of work with these numbers and ultimately figure out the specific heat of the metal. I'm going to start walking through the calculation, but if you think you've got this, pause the video, try it out on your own. Who cares if you get it wrong? Just give it a shot. It's really applying the Q equals MC delta T for the metal and for the water. Let's start walking through this calculation. I know that the metal decreases in temperature, so I've got the negative Q, and the water increases in temperature, so we'll have a positive Q. So I have negative MC delta T for the metal, and positive MC delta T for the water. Let's start plugging in what we know. I need a lot of room. So the mass of the metal was 40.5 grams. I'm solving for C. My final temperature was 27.7 degrees Celsius, and my initial temperature was 100.0 degrees Celsius. On the water side, 40.0 grams of water were used. 4.18 joules per gram degrees Celsius is the specific heat of water. And we went from a final temperature of 27.7 degrees Celsius, and the initial temperature was 21.5 degrees Celsius. I know I'm showing all of my work. If you wanted to simplify the temperature changes before plugging in, there's absolutely nothing wrong with that. I'm going to do that now. 40.5 grams, trying to find C. So that is negative 72.3 degrees Celsius. It's going to be equal to 48.0 grams times 4.18 joules per gram degrees Celsius times 6.2 degrees Celsius. All right, now it's really just a math problem. I've got my one unknown. I'm trying to solve for the specific heat of our metal, and we're going to hopefully use that to identify it. I would really recommend kind of showing your work in multiple steps. It's really easy to make one small careless mistake and end up with a pretty wacky number. So if I take 40.5 times 72.3, my negative signs will cancel out. I'd get 2928.15 C. You might want to use X as your variable. That makes it easier for you to kind of see it. And if I take 48 times 4.18 times 6.2, I end up with 1243.968. I'm going to divide both sides by 2928.15, and I end up with C equal to 0.425, and my units are going to be joules per gram degrees Celsius, the same as they were for the specific heat of water. All right. If you were able to handle that calculation on your own, excellent job. If you needed to follow along with me, that's okay. Hopefully you're kind of getting the hang of it now. So we know that our unknown metal has a specific heat of 0.425 joules per gram degrees Celsius. If we compare that to a list of knowns, you can just kind of like look these up online. I'll just write that down again. So here are, 5 common metals. Our metal has a specific heat of 0.425 joules per gram degrees Celsius. Which one seems the most likely? Hopefully it's pretty obvious on what you would do here. You know what you've got. Compare it to the list of knowns, and whatever one it's closest to is your best identification. So I would say in this case, it is really likely that you're working with nickel. Nickel has the closest specific heat to what we've calculated. So I would identify this metal as nickel. In your workbook, there are a couple of other questions. Calculate the percent error. You have the accepted value. Calculate how far off you are from the accepted. We assumed that this calorimeter is a perfectly isolated system. That is not the case. Brainstorm where the energy can be lost or gained. And finally, what effect does the system not being closed, or isolated is probably a better way to describe it, have on your data, and explain the answer? So we'll take some time to discuss that in class if you've got questions, but definitely kind of wrap up the thought experiment, if you will, with those 3 problems. All right, chemists, that does it for today. Thank you so much for tuning in, and I hope you found this helpful.